page 132. This is section 3.2. Yes, we're skipping section 3.1. I will explain in the lecture why. 15 through 29 odd, and I wrote here, Pascal's triangle, or the binomial theorem, will be very useful.
Okay.
And it'll come up when we do this, when we do an example here. It won't be useful in every single problem, but there are like 2 or 3 problems where it'll be very useful. You'll see what I mean by that when we do an example. So I'm going to go ahead and get rid of this part right here. Do you have the homework down?
Yes.
Okay, I'm going to go ahead and get rid of it for some room here. Okay. So, all right, how do I want to begin this? We already talked about why we might want to find the slope of a curve, whatever that means, right? And before this show, the example, like day 1 that I used was if the input here, if x were time, say, in hours, and if y, the output, were like a distance in, say, miles, then the slope would be what?
The speed.
It would be the speed, right? And we think about that, we're like, if you have the slope, in that case it would be miles per hour, right? Then the slope at a given point, which we'll get into in just a second, would be the speed. It would be if you're talking about time versus distance. More generally, though, you have your slope as your rise over your run, right? For any graph or any line, but we're trying to generalize this to curves now. And really what this is the change in your y value over the change in your x value. This is the capital delta, or capital delta. It's a Greek letter delta. That's capital, lowercase is that. And when you see it here, it means the change in. And so, we'll come back to that in just a second. What we want to do, and we've already talked about this, right? And again, it's not really the speed necessarily that we care about. We want to know, how does this function, whatever it is, how does it change? And this gives you a rate of change. Right? And the reason why I started with speed is we all kind of have a feeling for speed. We've all driven in a car before. And you have the idea that the faster you're going, the faster your place is changing. And it's kind of the same thing here, right? Like, well, let's do it this way. So another thing I've said is here at this point, this is not a line, and so we can't really talk about the slope there, but what we can talk about is if you were to draw a line that touches at that one point that we care about, and yes, it may touch at other points further out, because maybe the function changes and comes back down and touches the line a bunch of times. That's not what we're talking about. We're talking about locally here. Locally meaning nearby this point, it touches at one point. Do you remember what this line was called?
The tangent line.
Tangent line. And it kind of, because it like goes off on a tangent. And so if we want the slope at a point, right, what we're looking for here is the slope of this line. We want the slope of the tangent line. And I've said before, right, and we saw in the very first example that if we know the slope at every point, then we could find out information about the function, etc. Being able to find the slope at any given point is going to open up all kinds of cool things for us to do. So I've motivated it initially by talking about speed, but really, if you think about it, the slope of a curve at any point tells you how the function itself is changing, right? And so the steeper the slope gets, the faster it's changing, right? The more shallow the slope, the slower it's changing, as you can see kind of right here. If you were to draw a tangent line down here, you'd say that's a really shallow slope, right? And so it's not changing very fast there. Also, you could, I haven't, this looks like this slope is always positive, but a slope could be negative, right? And so a big negative would be it's changing very fast. A shallow negative would be it's changing slow. But knowing about the slope can tell you about the function. And a bunch of other things that we really, that will blow your mind. And so, anyway, okay. So, we're going to think about this, the slope of this line right here. So we've already selected a point, and we say we want this. We want to know how is this function changing at this point right here. And so we could think about that as a tangent line right there that touches at that one point. And just, I want to think about this a couple different ways. You could think about it as like I did, like the line that touches the curve at one place. You could also think about it like this. If this blue dot right there were moving along the function as you increase x, and if all of a sudden the function were to vanish at this point, which direction would it continue on? Right? Like its trajectory would be like that, right? And so you could think about it like that. Like if you have a ball on a string, and here's the string and the ball is coming along here, and then you let go of the string, which direction is it going to go? Well, it's going to continue on, assuming there's no other forces acting on it, and like there's not gravity and stuff like that, right? But like out in space, if something's moving like this and then all of a sudden all the forces are gone, which direction would it move? Move like that. Another way of thinking about this, we'll get into later, but it's kind of like if you were to zoom in on this, any curve, well, not any curve, most curves, and all the curves that we talk about in this class will have this property where when you zoom in on them, they look like a line. Right? So, for instance, I'll just go ahead and do this now. Let's just say we zoomed in right here on this box, and we made this much bigger. Well, and you'll do this in your homework, by the way. Number 15 will have you do this. And so I want you to go to Desmos and plot, you'll plot a function, and then you'll just zoom in. And you'll notice that as you start zooming in, right, okay, it's still kind of curved like that. So what you do is you zoom in some more on the point that you care about. Keep doing that, and you zoom in on that. And the more and more that you zoom in, eventually, this thing will look more and more like a straight line. And that straight line that you're looking at, once you zoom in sufficiently close, it will be the same line as the tangent line right there, right? And it's like, it's still kind of curved. Well, zoom in some more, right? And you zoom in some more, and eventually you will not be able to tell the difference between a line and the curve. It'll look exactly the same. And when you do that in Desmos, then what you're going to want to do is estimate that slope right there. So you have, and of course Desmos gives you, boxes and stuff. And so you could just count the number of boxes and you go, well, if I go over 1, 2, 3, I go up 1, 2, 3. Well, I guess the rise would be 3, the run would be 3. It would be a slope of 1. And you'll see that what we're about to develop right here is essentially, that's what we're going to do. We're just going to do it symbolically with mathematics and not so much with graphing software and stuff like that. But anyway, so that's a bunch of different ways of thinking about what a tangent line is. And it's not so much the line that we care about. Like our goal isn't to find what is this y equals mx plus b right here. Although that will be useful, and we will be doing that with some things. It will be really nice to have the equation of a line at that point. Right now, all we're interested in is the slope of that line. That's the thing that we're after. Okay, so you with me? Right? This isn't new. I'm just basically restating the stuff that I said in the very first lecture. All right? Okay, so we want the slope of this line right here. So the thing that we do, right? And let's make this concrete now. Let's say that this function is x squared. And let's say that this point right here is the point x equals 1. And so what we're going to do is we're going to estimate this slope, right? By saying, well, let's find another point further over here. And let's say that that point starts here at 2. Okay? And we'll estimate that slope. Okay. And so if that's the case, what's the output up here? If 2 is the input, it's 4. In other words, you take 2 and you square it, right? In fact, I'm going to do it this way. We're going to take whatever your input is. In this case, it's 2. You plug it into there. This says take 2 and square it, and so we get out a 4. Right? Here, we take whatever point this is. It happens to be 1. We plug it in, and we get f of 1. Plug in f of 1, that's 1 squared, which is just 1. And now we could find the slope of, it's not the tangent line. It has a name. This line right here, it's called a secant line. Yeah. We could go into why that's the case, but it is not necessary at all. And so we're going to find the slope of this secant line, which is going to be the rise over the run, or the change in y over the change in x. And in this case, we're going all the way to here. That's my change in y. And here, it's what? 4 minus 1. Okay, now the change in x is the distance from here to here. That's my delta x. And it's 2 minus 1. So that's a big 3 over 1, which is just 3. Nice. Okay. It's not a very good estimate, really. And you could see, just by the way I've drawn this line does not have the same slope. The green line does not have the same slope as the red line. So what do?
Make it smaller.
Right. We're going to bring, or we could say, another way of thinking about this is we're going to bring that point closer to the point that we care about. Right. I'm going to say, and which ones did I use? I used that one. So instead of going out to 2, maybe this time we'll half that distance. We go 1.5. So we plug in a 1.5. We get f of 1.5, which is 1.5 squared, which is 2.25. Yep, 2.25. Okay, so now we want to find this slope here. And now we have a new secant line. And you can see, hey, this secant line looks a little bit better. It's a little bit closer than the previous one. We still need the change in y over the change in x. And that right there is 2.25 minus 1. Now, what's that? That's 1.5 minus 1. So 2.25 minus 1 is 1.25. 1.5 minus 1 is 0.5. You work this out, it comes out to 2.5. Okay, and we see, and it's still not. The reason why we're skipping 3-1 is because it has you do this over and over and over again. And I think we really don't even need to. Like, I'm going to do this a couple times today. And really, we probably don't even need to do it a couple times because I think you get the point, right? So, like, the closer you get, the better the estimation is. So I plug in a 1.25. I get out a whatever 1.25 squared is, which I already did and calculated. It's 1.5625. 1.5625. Now, the slope and, of course, the secant line is an even better approximation. It's getting closer and closer to the thing we want. It's not quite there yet, but we have 1.5625 minus 1 as my new rise. All right, there's my delta y. My delta x is now, it's only from 1.25 down to 1. So that's 0.5625 over 0.25. Plug that in your calculator, and you get out a 2.25. It just happens to be nice like this. It's just, this is one of the few ones that just works out to be nice like this. And, okay, one last one, and I hope that after this, you guys are like, I never want to see this again. Because, yeah, this is the point. I don't think that you're going to get much out of doing this over and over and over again. But It's still not there, so we're going to go closer. And let's go, oh, how about to 1 point, did I do 1.1? No, I went for broke. I said 1.01. We're going to get really close now. Okay, so now we're at 1.01, so we're 1/100th this way. I plug in a 1.01 and square it, and I get out a 1.0201. And so, we can see, as we do this, our secant line is even closer. It's the slope of this secant line is getting closer to the slope of the red line, the tangent line that we actually want. And so, we say, okay, the new rise is 1.0201 minus 1, right? There, minus there. And now we have 1.01, the run is that, and we get 0.0201 over 0.01. Would you work that out? It should be 2.01. And it looks like it's converging to a value. Can you guess what that value is going to be? 2. It looks like it's going to be 2. It looks like the slope of the tangent line that we actually care about, it looks like it should be 2. Okay? Now, visually what we've done here is you've seen each time we're calculating the slope from here to, we started at this point. Then we calculated the slope from there to this point. We calculated the slope from there to this point. We calculated the slope from there. And we can imagine that the closer we get, the closer that slope is going to get to the tangent line. And so you think, okay, and so the book walks, section 3.1 walks you through about, 20,000 of these. Then you think, okay, now they finally cut to the chase, because what we're going to do here is say, all right, what's happening here is we're letting some value get smaller and smaller and smaller. In fact, we'd like it to be infinitely small. This sounds like a limit, right? And so then they say, okay, well now what we're going to do is, in order to calculate this value, what we're going to do is say that now the distance that you're going, we'll go ahead and call it h. So that now the total run that you have is this distance. From here to here, we're going to call it h. And so you start at 1, you add h, you're at 1 plus h. And so what does that mean for your output? How do you find the output there?
1.8. 1 plus h.
1 plus h, right. So whatever it is, whatever this function is, it happens to be x squared. But if we didn't know, you just say, well, you take 1 plus h and you plug it in. F of 1 plus h. Which happens to be 1 plus h, the quantity, squared. Okay? And so my rise is whatever that output is, right? I'm looking for, I'll keep this in blue. We're looking for the delta y here. My delta y over delta x, my change in y is that one, f of 1 plus h, minus this one right here, f of 1. Whatever that distance happens to be. And then my run is, well, 1 plus h minus 1, or we already knew it was h. That's kind of how we decided. We said the distance you go is h, and sure enough, 1 plus h minus 1 is just h. And so we have this right here, f of 1 plus h minus f of 1, all over h. And what we're going to do is take the limit as h goes to what?
0.
As h, and that's because that's what we're doing here. That's what we've been doing with these dots. We're saying we'll go some distance beyond it. We make it smaller and smaller and smaller and smaller. Can we let it go to 0? And that's the big question here. Is we want to know, is it possible to take the limit as h goes to 0 of this stuff? F of 1 plus h minus f of 1 all over h. Because as you look at it, you can't just plug in a 0. So hopefully, this is one of those limits where we could get rid of the h. And that's the name of the game now. If we could get rid of this h, or rearrange this thing somehow so that that h is no longer in the denominator, then we could plug in a 0 and we'll get an answer, right? So this shouldn't be too unfamiliar. So let's try and see what happens. This would be the limit as h drops to 0. Now, f of 1 plus h is 1 plus h squared minus f of 1 is just 1 squared all over h. What does your intuition tell you we should do here?
Multiply the 1 plus h squared.
Multiply it out?
Yeah.
Is that what you're saying? Yeah, and that's what I'm hoping. So I'm going to do that. First, outer, inner, last gives me what?
H squared plus 2h. Or, well,
yeah, and yeah, you could do it that way. I set it up. I like to set it up this way. 1 squared
plus 2h
plus 2h plus h squared minus 1 squared is 1. That's my h. That's nice because that 1 is now, that 1 cancels that 1. And now I get the limit as h goes to 0 of 2h plus h squared over h. What does your intuition tell you should do?
Factor out an h from the top.
Let's factor out an h. So I'm going to take the limit as h goes to 0 of h times, I guess we'll be left with a 2 plus h. Make sure I haven't messed anything up. Is that correct?
Yeah.
Yeah, I just factor out the 2. That would give me that. Okay, now I can cancel these guys. And I get the limit as h goes to 0 of 2 plus h. Can I just plug in a 0 for h now?
Yes.
Yes, right? Because this is a polynomial. It's a polynomial where your variable is h. It works out to be. And so, oh. Yeah, no. This is, woo! Okay, I'm getting ahead of myself. Yes, we can plug it in. You get 2 plus 0, which is just a big fat 2, which is what we'd expect here. You see what's happening? Like, they're setting up a limit, right? Like, and I think we could just cut to the chase. And just say, I feel that you guys don't need to do... Same way when you're doing limits before. They have you plug in a bunch of values and you see, yes, it's getting closer and closer to some value, and yes, that works. Let's just forget this part, okay? I think we can all just wrap our heads around this process. Now, okay, so now, what do we have? Well, we found the slope at the point 1. It's not just because the slope is obviously not the same everywhere. If you went here, it looks like the slope would be much closer to 0. The further out you go, the steeper the slope's going to be. But we can say here at 1, the slope of the tangent line, or as I'm going to say from now on, the instantaneous rate of change, right? At an instant, if you think about this as time and you choose 1 instant, what is the rate of change at that instant? It's going to be 2. And I'm going to put a little subscript here so we remember that the slope here at 1, when what instant are we talking about? 1, when x was equal to 1, you get a 2. Okay? But section 3.1 still beats around the bush. Because you think, okay, we've just cut to the chase and we could just do this. Then they give you a bunch that are like this. So I'm going to get rid of this. We saw, yes, the secant lines will converge to the tangent line. And you started with 3, then you go 2.5, then it goes 2.25, 2.1, 2.01, 2.0001, 2.000001. Yes, I get it. You're going to 2. And yes, we could just see that. In fact, I'm going to put this up here. We found that the slope of this function, and I'm going to say that. I'm going to say the slope of this function at 1, and what you know that I mean, is the instantaneous rate of change at 1. Also, you could say the slope of the tangent line at 1 was equal to 2. Okay? Okay, I'll use all of those terms interchangeably. Because technically, a curve doesn't, or a non-line, anything that's not a line doesn't have a slope. But I will say the slope of the curve. I will say the slope of this parabola at 1. I just do that. Okay. So then what your book's going to do is say, okay, now take this and find the slope of the tangent line, or the instantaneous rate of change, at 2. And you go, okay, well, 2 plus h, right? We're going to go with some distance h over 2 plus h. And then we're going to find the out, because we need a delta y, we need a delta x. And so my output is what I get when I plug in a 2. Output here is what I get when I plug in a 2 plus h. Now, f of 2 is actually 2 squared, which is 4. And this is, well, whatever 2 plus h squared is, because of this specific function that I have. And now what we're looking for is the slope here at 2, right? What we want to find is m, now the new slope here at 2. And so you do this, and you go, okay, well, it's the same process, right? We take a rise over a run, right? We're going to find our delta y over our delta x, and we're going to take the limit as the bottom goes to 0. Delta x goes to 0. Delta x happens to be h, the way that we set this up. And I will say, what we're about to get to, there's a bunch of different ways of formulating this. And I'll show you a few of them. But they're all equivalent. And this is the idea. Let the input get really small and watch what happens to this ratio. Does that make sense? Yeah. Okay. So in other words, in this case, what we're looking for is the limit as h goes to 0 of the rise, delta y, which is that one minus that one. So 2 plus h squared minus, I'll just go ahead and just write it as 4, right? Because you plug in a 2, you get a 4, okay? And then 2 plus h minus 2, or, oh yeah, the whole reason that we set it up that way was to have just h right there, right? Okay, same thing, and you're going to do this again. H goes to 0 of 2 plus h squared is what?
4 plus 4h.
4, right, because it's 2h plus another 2h for a total of 4 h's, then plus h squared minus 4. Hey, look at that, the 4's cancel out again. That's really convenient. I wonder if that's always going to happen. Limit as h goes to 0. Now we just have 4h plus h squared over h. The whole goal is to get rid of that h in the denominator, so I'm thinking factor out the h, that would probably help. So I'm going to take the limit as h goes to 0 of h times, it'll be 4 plus h all over h. Those guys cancel, and I get the limit as h goes to 0 of 4 plus h. Now can I just plug in an h? I mean a 0 for h?
Yes.
No problems there. It's going to go to 4. And so now the slope here, the slope of this function at 2, at the input 2, so the instantaneous rate of change of this function at the point 2 is equal to 4. Another way of saying that is that the tangent, if I took this function and I drew a tangent line right here and where it touches at 2 comma 4, and I figured out what this would be, right? If I zoomed in on there and saw what's the slope of that line, the slope of that line would be 4. Okay? Okay. So we're still beating around the bush. 3.1 still beats around the bush, and this is what it has you do for the rest of the time. I say, let's just cut to the chase. Who cares if this was at 1? Who cares if it's at 2? Who cares if it's at pi? Or, e, or 7 plus 9? I don't care. What we could do, and this is mathematics, we could just say, you know what? We're getting different values. It depends on what we're plugging in. What if we just, instead of plugging in an actual number, you say, you give me any number. Let's just call that number x. Right? Yeah. That's the great thing about math, is you could just say, well, suppose that you gave me a number. And instead of writing down a 2, I can say, well, whatever number that you did give me, there's my placeholder there. And so now what I'll do is I'll take that number, plug it in, and find an output. So it's whatever f of x is. I plug in the number that you gave me, and out pops f of x. In this case, it happens to be x squared. Now, whatever number you gave me, I'll just go h units to the right, And now I'm no longer at x, I'm at x plus h. And so I'll take that new number, whatever x plus h is, and I'll plug it in, and out's going to pop, well, whatever I get when I plug it in, x plus h. In this case, it happens to be that we have a formula for it. Cool. So I take x plus h, I plug it into that function, and it tells me that, well, take whatever it was, x plus h, and square it. And now we get the same thing. We could say, and it didn't matter where we started, right? The way I've drawn it here, it looks like we're at 1 or something. It could have been down here at -5. It could have been over here at whatever. Like, it could be a lot of different things. But that's the great thing about math, right? That's kind of the point. One of the points that we could do this. And so let's just do it. Let's just cut to the chase. And so the slope that we want then, right? That slope, it's the same thing. We're going to take the rise over the change in y over the change in x. And we're going to take the limit, right? We're going to take the limit as h goes to 0. So let's go ahead and let's just do that. Let's just say, okay, we're going to take the limit as h goes to 0 of the rise over the run. That's f of x plus h minus f of x all over x plus h minus x, which is just h, so I'm going to simplify and just say h, right? Yeah. Could have chosen any value that I wanted. Chose h for that reason, so that it's just that. And so let's compute this and see what happens. We're going to take the limit as h goes to 0 of f of x plus h is x plus h quantity squared minus f of x was x squared. The h is just an h. And let's do the same thing. What does your intuition tell you should do?
Multiply it out.
Multiply it out, and what do we get?
X squared
X squared
plus 2h.
2h.
Oh wait. First clue, 2xh. You got an xh plus another xh for a total of 2xh. I think when I did this, I did just put 2h, and then I got to the end and I was like, where did I go wrong? And yeah, I know what I'm doing. How did this happen? Because, yeah. Plus h squared minus x squared. Hey, look, it did. It did. It's always going to cancel. That's interesting. It does cancel out. The x squared there minus that x squared there. And now, you see what I mean? Why in this homework you might want to remember the binomial theorem? Because if you have, say, an x plus h to the third, you could waste a lot of time multiplying things out. Or you could say, wait, Pascal's triangle. Yeah. So it should be x to the third plus 3x squared h plus 3xh squared plus h cubed. Much easier if you remember that nifty little trick. Yeah, okay? Yeah. So we could cancel this x squared and this x squared to give us, okay, the limit as h goes to 0 of 2xh plus h squared all over h. Still can't plug in that 0. So I need to factor out an h. And so I factor out an h, and I'm left with 2x plus h over h. Those guys are gone. Now I get the limit as h goes to 0 of 2x plus h. Can I plug in a 0 now? Yeah.
And what do I get?
2x.
So now, here's the big idea. This isn't just the slope at one point. This is the slope at any given point. As a matter of fact, this thing that we have, this thing that we've just calculated now, is a function of x. This will tell you the slope of that function at any value of x, and it tells us it's equal to 2x. When I said, and so now let's just check this out. We said that the slope of this thing at 1 was 2. What happens if I plug in a 1 into this function? I get out of 2. Oh! What happens if I plug... We said that the slope of this function at x equals 2 was equal to 4. What happens when I plug in a 2 into this function?
You get a 4.
I get out of 4. this function, this is a function that tells me the slope of my original function at any value of x. Can we cut to the chase? Right? This is this chase. Can we skip the plug in 10 different values and see, yes, it's going somewhere. Then do it somewhere else and see, plug it in and see what to do. Yeah. This is the big idea here. Given a function, we could derive a new function which tells us the slope at any point, the instantaneous rate of change at any point on that function. Yeah. You with me?
Yes.
Okay, so, thing is, and now another thing, it's so much easier to just do this one time, right? Like, instead of, okay, I want to know what the slope of this thing is at 1, and you do all of this where x just happens to be a 1. Or, I want to know the slope of this thing at 2, well, you do all of this where the x is just a 2. Or, you do all this work one time, and now you have a function, and you just plug in whatever value you want. Seems like much easier, right? I mean, you can waste a lot of time doing. That's why I don't want to do 3.1 at all. I think it's just a huge waste of time. Let's just jump to it, right? This is the idea. And so now, you got. Can you lock this picture in your head for the rest of your life?
Yeah.
Okay. All right. Well, actually, I do want to keep it up. I do want to keep it up for just right now. So here we go. Definition. I want to use black. Definition. The derivative. The derivative of a function f is a new function called the derivative of f. And it's given by the following formula. Limit as h goes to 0 of f of x plus h minus f of x all over h. Now watch what I'm going to do. This is important. The derivative is written like that. It's a prime, f prime, and it said f prime of x. And so you're given some function f, you take the derivative, you do this, and that new function that you get, we're not going to call it m of x, we're going to call it f prime of x. But this was exactly what I did in the example just now. We said it's the, I was just saying it's the slopes, we think of slope as m, nobody uses this, I made that up. This is what it is. That new function that you got after doing this process is called the derivative, and we will also call it f prime of x. Now, but there's a caveat. For any value of x where the limit exists.
Oh, yeah.
Because there may be a value where the limit doesn't exist. This will usually show up like you'll get a formula like we just did, right? We took a function x squared and we got a new function. So when f of x was equal to x squared, we found that f prime of x, the derivative, was equal to 2x. And you could see that there's no problems here. Like you could plug in any value of x and there's no problems. You might have some function where you have some function and it's equal to something, and then you take a derivative of it and you get something like 2 over x. Well, there's one place where that doesn't exist. You can't just plug in a 0, and that's how you're going to know that the limit doesn't exist, really. I mean, that's how all of this works out. Okay? And it could be the case, and we'll see in a minute, that... So first off, what's the domain of this function?
All real numbers.
So the domain of f is all real numbers. What's the domain of its derivative? What is the domain of f prime? Also all real numbers. That's not always going to be the case. You might lose some numbers in the derivative. In other words, the domain may not be the same for all of them. It happens to be with this one, but you might lose something somewhere along the way. So another way you could say this here is that the domain of f prime, the domain of your derivative, the domain of your new function, the domain of your slope function, is equal to the set of x such that the limit exists. It exists, yes. I'm not writing the full thing out, but this is what we're saying. So this is another way of saying, this is a mathy way of saying for any value of x where the limit exists. Where it doesn't exist, well then it's just not in the domain, you can't just plug it in. So, not much going on there. Okay? Okay, now I'm going to do one more time. So, can I get rid of all this stuff?
Yeah.
This is what calculus is all about. At least the first half of calculus, this is what it's all about. This is the big idea. We could, given the function, not all functions do this. The functions for which you can do this are called differentiable functions. A function is differentiable if its derivative exists. You could say a function is differentiable at a point if its derivative exists at that point, etc. Not all functions have this property, but pretty much every function you've ever seen in your life does have this property. But we'll get into where functions that don't and blah, 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 blah. But yeah, okay, so here we go. Example. We want to find the slope of the tangent line to the function f of x equals square root of x at x equals 4. Now, I'm going to do it the dumb way, just to really, really, really force the point that we shouldn't ever do it this way. But here's the bad way. So I'm going to take my function, this is f of x equals square root of x. And I want to know when I plug in a 4, that right there, I want the slope right there. I want the instantaneous rate of change right there. And so, what I'm going to do is the same thing that we've been doing. Plug in my 4, I get out a what? 2. Now I go how far this way?
1 or 0.000.
Well, yeah. But we're gonna h.
Yeah.
Okay, and so we go to 4 plus h. Yeah. Right. So I'm setting up. By the way, I didn't say this. That the f of x plus h minus f of x all over h is called the difference quotient. It's a quotient. Yeah. And it's a difference, right? Both of those are differences. So it's a quotient of differences. It's a difference quotient. So I'm going to set up the limit of the difference quotient. That's what I'm trying to do here. And so, but when I plug this in, what do I get out?
F of,
yeah, there you go. F of
4 plus h.
4 plus h, which is what?
The square root of
the square root of 4 plus h. Square root of 4 plus h. Okay, and so I want my rise and I want my run. My rise, my delta y, is whatever the last one is minus the first one.
Yeah, so square root of 4 plus h
minus 2. And then down here, what's the run?
2. Or, no, h. Sorry.
H! Yeah, by design, it's h, right? So delta x is h. I'm going to take the limit as delta x goes to 0. So the limit as h goes to 0 of the top stuff. So f of x plus h minus, well, see, we're doing it the dumb way, right? So 4 plus h minus
2 over h. Can I plug in an h?
No.
No, I get 0 over 0. At least. And you see, one nice thing about limits, you know, and I think I've said this a couple times, is you plug in the 0 down here, and you get a 0. Obviously, that's bad. Plug in the 0 here, and you get root 4 minus 2, which is also 0. So there's hope, right?
Yeah.
If you plugged in that 0 and you got 3 over 0, there's no hope. You can't hope that, because if that's what it's going to, it's just going to get infinitely big.
Yeah.
And so there's at least hope here. And so, okay, what am I going to do?
Multiply the top and bottom with conjugate.
Yeah, there you go, right? So I'm going to go ahead and multiply by what I get when I do the plus instead of the minus. And so that's going to be 4 plus h plus 2, root 4 plus h plus 2. First, outer, inner, last.
So it's just 4 plus h.
4 plus h
Minus 4.
minus 4. Oh, nice. That's going to cancel out. And so I'm not going to bother to multiply that guy through, because it's just going to hinder progress here. And so the 4's are gone. That's the same thing as h over h times stuff. So I could cancel the h's. This gives me the limit as h goes to 0 of 1 over root 4 plus h plus 2. Can I now plug in a 0?
Yeah.
And I get root 4 plus 0 plus 2. What's root 4?
2, so 1 over 4.
So 1 over 4. Oops. 1 over 4. Okay, so what we just found was that the slope at the point 4 was equal to 1/4. Okay. Now let's say that the next question was, what's the slope at 16? Now you have to do all this over again. Well, what's the slope at 7? You got to do all this over again. So how about just in the first place, we could have just said, well, let's just do it in general. Then if there's any follow-up questions ever, we could just say, you know what? We have already figured this out, right? It will be, like, no matter what problem you have, even you could say, well, I'll just do it, I'll set it up at 4. Or you could just do it in general, and it'll be fine that way, right? So
It's just as much work, and then
it's exactly as much work. But then once you've done all of this work, now you can answer a ton of questions. And maybe you only need to answer one. Okay, it's the same amount of work. Just do it in general. Do it with your so anyway. That's my spiel. And now let's actually do it. I plug in an x, I get out a root x. I plug in x plus h, I get out a root x plus h. And I get something now when I set up my difference quotient that should look very familiar to you guys. We want to take the limit as h goes to 0 of root x plus h minus root x. That's the rise, that's the delta y. You take the one on the right minus the one on the left over the one on the right minus the one on the left, which by design is just an h. And so now we're going to say, oh, wait, can't plug in an h. So let's do our nifty little trick with the numerators and the with the conjugates. Do it in the numerator and in the denominator. It's going to look very familiar here in just a second, because we get first, outer, inner, last gives me first, outer, inner cancel, last gives me a minus x. Oh, that's nice. Root x plus h plus root x. Now, the x's cancel. I'm feeling a theme here. The h's cancel. Nice. And I get the limit as h goes to 0 of 1 over root x plus h plus root x. Can I plug in a 0 now?
Yeah.
So let's do it. That gives me 1 over root x plus 0. Root x is a total of 1 over 2 root x, which both of you guys got on, this was the problem on the quiz.
Yeah.
Both of you guys got this. So now we could say, okay, now our derivative, f prime of x, is equal to the function 1 over 2 root x.
Now I could just say, well, if you want to know what's the slope at 4, I'll just plug in a 4. And let's do that. F prime of 4. In other words, the slope of this original function f at the number 4 is going to be 1 over 2 times root 4, which is 1 over 2 times 2, which is, lo and behold, we got the same thing. Isn't that nice? And so, there's your answer. I suggest we just forget about finding individual points. Let's just move on to cutting to the chase and saying, if you do it in general, it's exactly as much work. It might be a little weird. It might be a little bit harder because now you have x's instead of like a 2, but it's worth it. Okay. Any questions?
No.
Okay. All right. So I already said this, but I didn't tell you what it was called. Another way to think about the whole, and you notice like with the whole zooming in thing that we've done, or this process of taking h to be a smaller and smaller number, right? As h gets smaller and smaller, your secant line gets closer and closer to the tangent line. Another way of thinking about that is that's kind of what you're doing when you zoom in. Right? When you start with this picture right here and you zoom in on it, the original thing that you have is a curve. It's still curved, right? And this is kind of like saying, well, what's the slope from those points right there, right? As you have a bunch of other points. And that's the point that you care about. So what you do is you say, well, let's zoom in some more here. And you zoom in right here. And you blow that up. Now you have something that looks a little less like a curve, a little bit more like a line, and you're kind of estimating now the slope between these guys. And so this process where we plugged in a bunch of numbers and we had 3, 2.5, 2 1/4, 2.01. This is basically what you're doing. This limit or this process of taking h to be a smaller and smaller number is exactly this process of zooming in. This is what we're doing. We're just doing it symbolically, right? And we're doing it with a formula that will tell us what we get, right? Until eventually it does look like a line. And you could say, we are close enough now that the rise over the run really does look like a quarter. Well, I've drawn it to look different, but you get the idea, right? Okay. Next time, how are we doing? Oh, we're good. Okay, we'll do one more example, but next time we're going to get into the geometry of this stuff. I'm not even going to bother right now, but you could see. So first off, what's the domain of f here? The original function, the domain.
Real numbers that are 0 or bigger. Like,
can it be equal to 0?
yeah.
Yeah, we can include 0. Now, what's the domain of f prime? The derivative.
This. Wait. No, it's just all real numbers. No, yeah, it's the same. All real numbers that are greater than or equal to 0.
Can it be equal to 0?
Oh, no.
No. And so we've lost a point.
Interesting.
Yeah, it happens. It happens with derivatives. You might lose a point. It used to be the case that you could plug in a 0. But now think about what what does that mean? If you divide by 0, what happens to the thing? It blows up, right? And if you look at this, as we get closer and closer to 0, what's happening to this tangent line? It's getting
closer to like a straight up and down.
Yeah, and so in other words, out here at 4, the slope was 1/4. At 1, the slope would be 1/2. At somewhere else, it's gonna, as this gets smaller, then the thing itself gets bigger, right? And it's getting bigger and bigger and bigger. And if you try to plug in a 0, well, there's no derivative there. The derivative doesn't exist at 0. And then what this is telling us graphically is that the tangent line is becoming a vertical line, right? Like that doesn't. You get infinity. The slope there would be infinity, which isn't a thing, and so we say it does not exist. It's not in the domain. We'll get into the geometry of these things, and like half of what we're going to do, a quarter of what we're going to do this year is going to be looking at the geometry of f, looking at the geometry of f prime, and seeing how they're related. It's, again,
It's like with like
so useful.
sine or something, every time it crosses 0, would it do that? Because like this tangent line is getting...
Well, not at 0, because it never goes straight up and down. It kind of comes through like this, sine does.
Oh.
It's kind of like negative
Yeah.
and positive. And so sine and cosine are fine. But something like square root, right? It is straight up and down there.
Oh, yeah.
Because if you think about what is a square root, well, it's kind of like the inverse of this function here,
Yeah.
right? And so it turns out, remember, with this, if this was f, we found that f prime, the derivative, was 2x. Here at 0, when x is equal to 0, then the derivative is equal to 2 times 0 is 0. So the slope of this line right here is 0. And so flipping this guy up this way would give you a slope of infinity, right? And so, yeah, so we'd say the derivative doesn't exist there. Or it has no derivative at 0. Again, we're going to get into this on Thursday. We will get way into all of that. I'm going to give you... This is so hard. Oh my goodness. I want to do this because of how hard it is. I messed it up so bad too, and I was like, how did I mess this up? F of x. So this is 24. Basically, that problem 15, it's you graph it, and you're going to do a bunch of stuff like that, and then you'll finally just take the limit, etc. The other ones are all, they give you something like this. They say, okay, here's your function. Is that a minus 3x? And we want to find its derivative. Find f prime. And so we're going to go straight to the definition. We're going to take the limit of the difference quotient. And so we'll say f prime of x is equal to, and I'm going to go ahead and write it in general here, right? In general, it's f of x plus h minus f of x all over h. So that's the same thing as the limit, as h goes to 0 of, it's going to get ugly. So 3 plus x plus h minus 1 minus 3 times x plus h. Notice how parentheses are your best. I've been saying this since Algebra 2. Parentheses are your best friend. I've been telling you that this long because of this right here. Over 1 minus 3x all over h. Can I just plug in an h? I mean a 0 for h? No, because that guy. So hopefully, and so a bunch of different ways we could go with this. One thing I'm going to do real quick before we begin, just to save some space, I'm going to go ahead and distribute this negative 3 into here. So minus 3x minus 3h. Minus 3x minus 3h. And now I'm going to say, okay, look, I have denominators inside of a fraction, so I'm going to kill those denominators. I'm going to have to, come on, 1. And so I'm going to have to do it to the top and the bottom. And those denominators are simply 1 minus 3x minus 3h, 1 minus 3x minus 3h times 1 minus 3x. 1 minus 3x minus 3h, 1 minus 3x, on the top and the bottom. Now, okay, so this jumps over, that one kills that one, and I'm left with, let's see, it'll be whatever's in the numerator, 3 plus x plus h times 1 minus 3x. Minus, that one kills that one, so he's gone, and now we just have 3 plus x times that one. So 3 plus x times the ugly one, 1 minus 3x minus 3h, all over h times that stuff. 1 minus 3x minus 3h times 1 minus 3. And you'll find in this class, the hardest part of calculus is the algebra. Everybody agrees on this. This is the hardest part of the class. Because I think you get the idea. That's some function, and we want to find what's its slope. Like, that's all there is to calculus. It's like, let's just find this new function that'll tell me the slope of this thing. That's all there is to it. This is the hard part.
Yeah.
Like, this is just ridiculously hard.
Factor out the 1 minus 3x minus 3h.
You could. Could we do that? You want to do that? Yeah. I've had so much experience with these that I know that's probably going to go in the wrong direction. What?
Multiply by the conjugate? I don't know.
No.
Multiply them out?
Multiply them out.
Okay.
That's usually going to be your best friend.
But not the
1 minus 3. You can't factor out any of those anyway. You can't factor that one out because it's not over here. Can't factor that one out because it's not over here. So,
oh, yeah.
Yeah. And so usually you want to multiply these guys out, which I'm going to do real quick here. So I'm not going to have enough room for that.
Multiply the bottom out as well.
So limit
But not the h.
as h goes to 0. Turns out the bottom I'm going to want to keep like this. Okay, so now this negative's going to mess your world up too. So the 1 jumps in and just gives me a 3 plus x plus h. The negative 3 comes in to give me a negative 9x. Negative 3x squared. Negative 3xh. Now, I'm going to do it like this. Minus all that stuff. So minus each one of these. Now the 3 is going to jump over and give me a 3 minus 9x minus 9h. X is going to jump in to give me a plus x minus 3x squared minus 3hx. And now let's see what could cancel. We have a positive 3 minus a positive 3. Good. I have a positive x minus a positive x. Good. I don't have a single h. I have a minus 9x minus a minus 9x. I have a minus 3x squared minus a minus 3x squared. So those are gone. I have a minus 3xh. Did I get that? Did I do something wrong?
Yes.
Okay. Minus 3xh minus a minus 3xh. So those are gone. That's gone. Now I get my limit as h goes to 0 of h minus 9h. So that's the same thing as a plus 9h.
Well, that was nice.
h1, and yeah, hey, that's nice. 1 minus 3x. That h factors out. And that's the whole point, right? Because every step along the way, can I plug in a 0 for h? Not yet. And so I'm going to say limit as h goes to 0 of h times 1 plus. Well, I could have written that as 10h, right?
Yeah.
That's 10h. So I'll just write it as 10h. In fact, I'll do that right back here. H plus 9h is in fact 10h. Now I can cancel that h. And I'm left with 10 over 1 minus 3x minus 3h, 1 minus 3x. Now can I plug in a 0 for h?
Yes.
Yes, I can. And what I get is a 10 over 1 minus 3x minus 0, 1 minus 3x. And so I could simplify that. That is the answer, but now I could write it a little bit simpler, like this. And so, given that f, this thing right here is f prime. That is the derivative of f, right there. Now, I'll tell you, we're only going to be computing derivatives like this for like a couple days. After this, so you remember like with limits, we did a bunch of stuff and we had to, well, one thing we didn't even do was like, you could use the rigorous definition to prove these things. But then we said, you know what? We could use the rigorous definition to prove limit laws. And then from those limit laws, we could simplify everything, right? Which is what we've been actually doing here, right? We say, well, do you see an epsilon or a delta anywhere on here? No, because we cut to the chase. We said, you know what, you could, as long as everything's fine, that's a continuous function, yeah, that's a continuous, yeah. We're not even saying that anymore, right? It's just like, obviously there's no problems. This is continuous, that's continuous, therefore, I could just plug in a 0 for h. Cool, and then you get this. Nice. Same kind of thing with derivatives. We're gonna do this for a minute, and then we're gonna get new laws involving derivatives that will make our lives much, much easier. And in the future, the short future, when you see something like this, you will not do it this way anymore. You're going to use laws for derivatives to say, wait a second, that's a quotient. I'll do something with the top, I'll do something with the bottom, blah, 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 blah. And you kind of notice how this thing kind of looks like that thing. That's not a coincidence. Like, there's a much quicker way to get from point A to point B. And so it's the same kind of thing. But at first, we're going to do it the hard way and be very careful with parentheses and signs. And I will say right now, and I know you're not here right now, Victor, but you better be listening to me. You have answers in the back of the book. If you do some stuff and then your final answer doesn't match with the one that's in the back of the book, you are to redo it until you get the right answer in the back of the book. Okay, there's not going to be too many of these in the future, but you need to go through these to see that yes, indeed, this happens. And then later on this year, not too far from now, we're going to use our laws for derivatives to do this a different way, and you'll see, oh, yep, it's the same thing as if I had done this. But this is really good exercise to make you believe that what we're about to do is indeed this thing. Because this is the definition. This is what you're actually doing. This is kind of like your epsilon delta for a limit. But then once we get to a certain point, we're not going to do it anymore. So, good?
Yeah.
Okay, so make sure your answers on this homework match with the answers in the back of the book. You are to check the back of the book for every single one of these. Okay.